Good morning, my dear students. Good morning. Nice to meet you all today. Okay. Very good morning to all of you. Right? They have been joining. Students one by one joining. It's good. Right? So, okay, I will start the class. Just a few minutes. Yeah. So, I will share the notes for today class. Right? Today we are going to discuss very interesting thing. Right? See here. Formulation of actually the unit 5 as per the previous syllabus I have written. Okay, forget about it. Almost 4 unit I have covered because the topics discussed not how to say particular unit. There are spread manner it is there. Okay, just see. Most probably it will come in 3rd unit, 4th unit and all. Formulation of strain displacement matrix. Okay, so we are going to see how to formulate strain displacement matrix. I am going to explain what is strain displacement matrix, how to formulate it, and element stiffness matrix for 1 and 2 dimensional problems in structural engineering. Okay, as per the syllabus I have written that I have given that title here. Okay, formulation of strain displacement matrix and element stiffness matrix for 1 and 2 dimensional problems in structural engineering. Formulation of element matrix for 1 dimensional and 2 dimensional problems in structural engineering. Okay, that is we are going to see strain displacement matrix and stiffness matrix here. Okay, how to develop a strain displacement matrix and then how to obtain the stiffness matrix for element stiffness matrix for each element, 1 dimensional element, 2 dimensional element, and all we are going to see in detail. Okay, so here I have given another heading: element strains and stresses. Okay, how to obtain elements strains and stresses. You are going to get a strain displacement matrix and then element stiffness matrix. Then we are going to write equilibrium equations. By solving it, we are going to get element strains and stresses. Okay, some discussion on element strains and element strains and stresses. I want to have some discussion. Okay, before that, the strain displacement relation. Okay, the strain displacement relations of the theory of elasticity could be used to derive the relation between the strains at any point inside an element in terms of the nodal displacement. Okay, so what we are going to do, we are going to obtain the strain displacement matrix, okay, which will relate the strain within the element in terms of the nodal displacements. Actually, the strain displacement matrix is the matrix which relates, right, the strain in the element and strain within the element and the nodal displacements. Okay, as you had a shape function. Shape functions, they relates the variational displacement within the element in terms of the nodal displacement. Okay, it relates shape function, but strain displacement matrix relates the strain within the element. It means the change in variation of displacement with respect to distance, or variation of displacement per unit length. Okay, that is, we call it as strain, right? That we are going to express in terms of nodal displacements. Okay, nodal degrees of freedom. The matrix which relates is called strain displacement matrix. Okay, if epsilon vector is the epsilon is the vector of strains at any point inside an element. Okay, now see here, epsilon vector is equal to, say, any element, you use small u to represent variational displacement within the element. Now I am using epsilon to represent the strain within the element. You, for example, you take 1 dimensional element. There's a strain within the element. I am using the notation epsilon. So epsilon is a vector. Okay, epsilon vector is equal to I am going to say some strain displacement matrix, say B. Okay, strain displacement matrix B into du, d suffix u, which is nodal degrees of freedom. That is nodal displacement vector. Okay, already you have u equal to u vector is equal to, that is the variational displacement. Otherwise, displacement vector is equal to n. Okay, a shape function into nodal degrees of freedom. That that relationship, you know how to develop shape function for various elements. We have seen in detail. Okay, now we are going to see how to obtain strain within the element. Okay, so there is a matrix relate. How do we obtain it? I will tell you. Okay, where B is called the strain displacement matrix, right? That's what, and will be functions of derivatives of shape functions n. Okay, please listen here, where B is called the strain displacement matrix and will be functions of the derivatives of shape functions n. How it will be functions of derivatives of shape functions n? Please, all of you see here, we know the variation of displacement within an element, that is the displacement in the element, u is equal to n shape function, okay, matrix n into du, null degrees of freedom vector. That relationship you know. Now, what is strain? Dou u by dou x. It means u is there, no variation displacement within element. It's change with respect to distance, no. That is called a strain, we call it as, or change per unit length is called strain. How do you obtain strain? Once the displacement is known to you, you have to differentiate it. You have to obtain the derivative of it. Okay. So dou u by dou x is the strain epsilon. That is equal to n is there, no. So dou n into du, nodal degrees of freedom. So the derivatives of shape function. Okay. So the shape function is we are applying derivative of shape function. That we call it as strain displacement matrix. That's what. And it will be a functions of derivatives of shape functions n. Okay. Okay, we will discuss further. This way we can obtain the strains in an element. Okay, in that we come across this strain displacement matrix. Very good. And then I want to discuss about the stress in an element. If epsilon vector is the vector of stresses corresponding to the strains epsilon vector. Okay, the element stresses can be expressed. Once the strain is known, how do you obtain stress? Stress equal to Young's modulus into strain, isn't it? Because stress by strain equal to Young's modulus, therefore stress equal to Young's modulus into strain. Okay. Now, sigma vector, that is a stress vector, is equal to C. Okay. It is nothing but elastic constant. That Young's modulus, like capital E is there, no, in one-dimensional element. Young's modulus, we call it as C. Why C, capital C? It is called constitutive matrix, constitutive relationship. The stress-strain relationship is also called a constitutive relationship. You may be aware of it. Okay, constitutive relationship, right? Stress-strain relationship. So, Young's modulus and all, Young's modulus is a factor, okay? It's a constant which gives the relationship between stress and strain. Stress between strain equal to Young's modulus, isn't it? So, stress-strain relationship. So, constitutive constant it is, okay? So, C. Elastic constants are called a constitutive matrix. That's why capital C I have used here. That into epsilon. Epsilon is B into du. B into du. Okay. Sigma equal to elastic constant matrix into epsilon vector. Epsilon vector is nothing but B into du vector. The u is missing, please. Du notation we use to represent null degrees of freedom. That is displacement at the nodes. Okay. That's what. C into B into du. Okay, vector. Right, where C is the constitutive matrix. That expression I given here is not necessary. Okay, whatever I told you is written in another way. Where C is the constitutive matrix. Okay, C is called constitutive is nothing but stress-strain relationship. Okay, Young's modulus represents stress-strain relationship. Stress by strain equal to Young's modulus. Okay, that's what. It consists of going to be elastic constitutive matrix here, constitutive matrix, right? So epsilon, let it be like that. Now we are coming to the important how to get this B, strain displacement matrix B. Okay, the discussion comes here. Okay, right here. Okay, so first you take a truss element that is one-dimensional. Truss element, if you choose x-axis along the member, axial element, truss element, otherwise axial element. Okay, I can say axial element means only deformation in the axial direction. You take a element, line element. That if you say take the x-axis along the element, we call it as one-dimensional. Okay, if the same element is kept in xy coordinates, okay, plane element, two-dimensional element. If it is in space, three-dimensional element. Okay, or arbitrarily oriented truss element, it's okay. You take a one-dimensional truss element. Okay, axial element, right? So there are two nodes. Here the displacement is u1, nodal displacement is u2. Okay. So, we know u equal to the variation of displacement within the element at any point, u equal to n into du. Okay, u equal to n1, n2 into u1, u2. This way we can write. First, u equal to n into du. That is nothing but there are two nodes, so two shape functions are there, n1, n2 into null degrees of freedom, u1, u2. Okay, this way we can write. Now, I am getting the strain dou u by dou x, which is nothing but epsilon vector. Okay. The strain in it is equal to dou n1 by dou x, okay, dou n2 by dou x into du, null degrees of freedom. All right. Now we are expressing the strain okay, in terms of the nodal degrees of freedom. So the matrix which relates these two, strain within the element and the nodal degrees of freedom, okay, the displacement of the nodes, is called a strain displacement matrix. This is called strain displacement matrix. Okay, that is nothing but B equal to the strain displacement matrix. B is equal to dou n1 dou x dou n2 dou x. Okay, that's what. Derivatives of shape function. Derivatives of shape functions is called a strain displacement matrix. Okay, so I told you how do we obtain it, right? Now we are for a one-dimensional line element. Already we have derived a shape function n1 equal to 1 minus x by L and n2 equal to x by L. Okay, therefore dou n1 by dou x equal to minus 1 by L. Dou n2 by dou x equal to plus 1 by L. Okay, that is there. Therefore B matrix is equal to minus 1 by L, 1 by L. Okay, yeah, that is dou n1 by dou x. No, this one is minus 1 by L. This is we obtained plus 1 by L. Okay, so we got the strain displacement matrix. So we have taken a very simple problem, one-dimensional line element, two-nodal line element I have taken, and I told you how do you obtain that strain displacement matrix. Okay, it's nothing but its derivative of shape function. Okay, now we are going to see how to develop or derive element stiffness matrix. Okay, element stiffness matrix, just some write-up is there. I will just read out, right? Just listen. Just for what is there, let us see. Thus, the element strains and stresses have been expressed in terms of, that's what. Thus, the element strains and stresses have been expressed in terms of the nodal displacement through the use of strain displacement matrix. Okay, just now we discussed. That's what written here. It can also be noted that once the shape function for an element is derived or obtained, the B matrix, that is strain displacement matrix, can be evaluated. No doubt. Yeah, you have just now you have seen the above discussion, right? Now it is necessary to derive the equilibrium condition for an element, which would help us to build up the condition for the assemblage of elements constituting the body or structure. Okay. Now we have to write equilibrium conditions, equilibrium equations. For that we require element stiffness matrix. How do we get it? Okay. For that, principle of virtual displacements and principle of stationary potential energy, which establish conditions of equilibrium for displacement formulation. This one. So the principles of virtual displacement, using that we can obtain from the basic principles of structural mechanics, K into D equal to Q. You are aware of it already. In matrix method of structural analysis, you have studied stiffness matrix method. You have studied K into stiffness matrix into D is equal to, it's a basic of structural mechanics, principle of structural mechanics. Okay, into D is equal to displacement. Okay, stiffness into displacement is equal to force. You know that. Q, small q. Why you use small k, small d, small q here? Because it is at the element level, right? That's why I'm using small letter. When it comes to global, use capital letters. Okay, so element stiffness matrix small k into du. Okay, displacement vector is equal to that is nodal displacement vector is equal to force vector, right? Force at nodes, right? Force acting at the nodes. This is a nodal displacements vector du or d suffix u or d something, right? That's what. Here, see here, explanation is here. That's what. K is stiffness matrix for the element. Q is the nodal vector. Now, how do we obtain element stiffness matrix? For that, some discussions are there, theory, that is going to be tedious, that is not necessary. The derivation I did not do. Okay, just I will tell you only the final form of the theory. That is, if you want to get, please, I advise you to memorize this one. For a three-dimensional body, right? If you want to obtain element stiffness matrix, small k matrix is equal to triple integral, because it's a volumetric integral, no? Three-dimensional body. That's why triple integral. This B transpose, that is strain displacement matrix only transpose into constitutive matrix into again strain displacement matrix B into dV. Okay, suppose if it is a two-dimensional element, what will happen? Instead of dV, we will be getting dA here, only double integral. If it is a one-dimensional element, k equal to only single integral, you will be getting dx here. Okay, this is for three-dimensional, k equal to triple integral B transpose C matrix, constitutive matrix into again strain displacement matrix into dV. Okay, If it is a, again I am telling, if it is a two-dimensional element, what is dV? Okay, you will be getting dA, okay, length into dA, and then for line element, area into dx, okay, dx, you will be getting dx here. Volume is area into cross-sectional area into dx, okay. Like that you will be getting here, okay. Accordingly, you have to use this formula expression. I will tell during the discussion. I will tell you again, okay. But you will memorize it. But we need not go into the derivation of this one, okay. The theory behind it not necessary for it. Just you memorize this expression, which is very, very important, right? To develop element stiffness matrix, we are going to use this one, okay, which is very, very important. Right. Now, this and all some other discussion, not necessary. Leave it. I will come to the continuity. Now, element stiffness matrix for one-dimensional element. We have seen that two-noded line element, no, one-dimensional. For that, we obtained a strain displacement matrix here, isn't it? We got the strain displacement matrix. Now, I am discussing further. How do we get element stiffness matrix for it? Okay, from this, from using this expression. Let us see. See, assuming that the area of cross section is constant throughout, no doubt. If you take a one-dimensional line element, two-noded, the area of cross section will be constant throughout. Okay, therefore dV equal to A into dx, area of cross section into dx. Therefore, the element stiffness matrix K equal to already I told you triple integral. No, since dx alone is there, only single integral 0 to L. The length varies from 0 to L in that element. See, okay, area I have written here, dx I have written here, because dV is A into dx. A is here, dx is here. Okay, now I am coming to the B transpose. What is B transpose? Strain displacement matrix transpose. Already we have seen strain displacement matrix is minus 1 by L plus 1 by L. Okay, its transpose is minus 1 by L, 1 by L. Okay, into constitutive matrix. It's a one-dimensional element. So the constitutive constant is Young's modulus. Okay, that's why capital E I have written. No need to put matrix and all, because single, only one. Okay, elastic constant is only one. So E into again B matrix. This one I am telling. Single integral A into dx I have written. B transpose I have written here. Okay, into constitutive matrix is only Young's modulus for this one-dimensional element, and then again strain displacement matrix B I have written here. Okay, into dx. Now you do that, do integration. A constant, that's why I have written AE. Okay, these two are multiplied. Okay, only integral dx is there, which is x. If you substitute limit 0 to L, it becomes L. This and all constant. Just you are multiplying. Okay, if you integrate the dx x, substitute as upper and lower limit. Okay, upper limit minus lower limit. So L alone is there. If you multiply these two, you are getting C. Multiply these two. How do you multiply? Minus 1 by L into minus 1 by L. So plus 1 by L square. Okay, again minus 1 by L into 1 by L. Okay, so minus 1 by L square. Next you take this 1 by L. 1 by L into minus 1 by L. Minus 1 by L square. Here you have to write. Okay, again 1 by L into 1 by L. So plus 1 by L square written here. Right? L is there. Okay, so write down AE by L. AE by L. Okay, now because here this is AEL, this L square take it outside, so L get cancelled, only one L is there in the denominator. That's why AE by L into 1 minus 1 minus 1 1. You obtained the element stiffness matrix for this line element, one-dimensional element, axial element. Already you know prismatic bar in the stiffness matrix you have studied. Okay. For a prismatic bar, okay, axial tension, what is the stiffness matrix? You know, AE by L into 1 minus 1 minus 1 1. Okay, you obtained the stiffness matrix for it. Already in matrix method of structural analysis, you have developed it, you studied, you know, you are aware of it. Okay, see, we got it. That's why we have done all this step function. With a simple example that one-dimensional two-noded line element, I am explaining, I have explained to you just now how to obtain strain displacement matrix. From that, how do we derive this element stiffness matrix for it? Okay, using this expression, we have used it. Okay, so very important theory we have seen today, right? Just for example, I have written another one also. Examination point of view, it is not important, just for your understanding. Okay, let us discuss further. Three-nodal element. Already we obtained the shape function for three-nodal line element, N1, N2, N3. Don't worry. Nobody will ask you derive element stiffness matrix for three-nodal line element. Nobody will ask you. Don't worry. Just for a discussion. Let us have a discussion. Not in the examination point of view, just for our understanding point of view. Okay, you know these shape functions and all for a three-nodal line element. Okay, therefore its derivatives dou n n1 by dou x, dou n2 by dou x, dou n3 by dou x, I have written here. Okay, therefore I have written here. Therefore B matrix is equal to dou n1 by dou x, dou n2 by dou x, dou n2 by dou n3. It's not there 2, dou n3 by dou x. Okay, so its value written here. We obtained the derivatives. No, the derivatives of shape function is written here. Thus, we obtained the strain displacement matrix for three-nodal line element. Therefore, K equal to volumetric integral B transpose in the constitutive matrix B into dV. dV equal to A into dx for that line element. Therefore, A into constitutive matrix is capital E. Dx is here. Okay, so the B transpose I have written here. So the B matrix, strain displacement matrix is written here. Okay, this way we have to do it. Okay, if you integrate dx L, you will be getting L alone. Okay, if you integrate integral 0 to L dx will give you L. Okay, if you substitute upper limit minus lower limit L, and you have to multiply these two matrices. Okay, thus this discussion I have given is not necessary. Please skip this one. Okay, if you want to go through leisurely later, just I am coming to this one from that where yeah, it's here. Yeah, so K equal to AE into this way we obtained element stiffness matrix for the three-nodal line element. Okay, so I have shown this way we can obtain it, right, by multiplying these two. You know how to multiply two matrices. That and all I need not teach you. Otherwise, you revise matrices. Okay, how to multiply two matrices, you will revise from your matrix. In the Google, if you search, you can get how to multiply two matrices. You will be understanding this into this. Okay, you have to write here this into this. Second first row sine column. Okay, this into this third column in the first row. Okay, this into this sine row first column. Okay, this into this what is that, sine row sine column. Okay, you know this into this you have to write here, this into this you have to write here, this into this here, this into that here you have to write. I hope you can understand. Okay, you know how to multiply two matrices. You will be getting 3 by 3 matrix if you multiply these two matrices. Okay, thus you obtained it. This is not necessary, just for your just I am telling how do we obtain element stiffness matrix for even a three-nodal line element. Just I shown, not in examination point of view. Okay, next we will go for the two-dimensional beam element. Okay, I will just discuss here in two-dimensional beam element. I will tell you how to develop shape functions. Okay, how to derive stiffness matrix, we will see it in the next class. If time permits, we will see now. Otherwise, I will continue. Now let me to finish shape function. Okay, two-dimensional beam element. There is a beam element. Okay, this skip. Okay, don't refer this sketches. I striked out already. Okay, don't refer it. I striked out. I have started freshly here. Okay, yeah, it's not necessary. I have started freshly. Okay, it's here. Two-dimensional beam element. Derivation of shape function first we will see. So two-dimensional beam element I have taken. First we are going to see derivation of shape function for it. Okay. Afterwards we are going to see how to derive element stiffness matrix for it. Right. First, a line element with two end nodes. See, two-dimensional beam element we are using line element only, but the node degrees of freedom we are assuming differently. Please see here, a line element with two end nodes can be used to represent the bending behavior, and each node can have 2 degrees of freedom, namely a translation and rotation. That's what. See here, I have taken a line element. Here node 1, node 2. In axial element, we have seen only the deformation in the axial direction. That's why you have taken U1, U2. But it is a beam element. In beam element, the same line element, but the node degrees of freedom we are taking differently. What is that? In the vertical direction, translation. Here also in the vertical direction translation, say W1, W2, because in Z direction W, no, X direction U, Y direction V, Z direction W. That's why W1, W2, and theta 1. Okay, clockwise, theta 1. clockwise theta to rotation. See, I have chosen here x. The downward is z. My y is perpendicular to monitor, but in which direction? Whether y is towards me or away from inside the monitor. Y is directed, positive y axis is directed perpendicular to the monitor, okay, but inside the monitor. Direction is positive, direction is inside the monitor. How? You take a right-handed threaded screw, keep it at top, rotate it turn it from x to y, okay. So the right-hand screw will move downward. So that represents positive z direction, positive set of Cartesian coordinate. How to choose? Okay, this is x. My y is perpendicular to the monitor, but inside the direction is positive, direction is inside the monitor. Okay, that is why if I take a right-handed threaded screw, if I turn it from x to y, okay. No. Have I told you correctly? Okay, no. Towards me, no. Towards me means right. Towards me, no. Yeah, it's okay. Forget about the set and all. Not necessary. That discussion not necessary for you. Okay. X is that whether positive y is towards me or inside me, forget about. It is perpendicular to the monitor. Okay. So I have chosen z axis like this. Sorry, this rotation theta1, theta2 like this. No degrees of freedom. Okay. Here no sign convention at all. Not necessary. Right. Let x and z be the spatial coordinates. Okay. That is global coordinates. Spatial coordinates means global. Let x and y, z be the global coordinates, and theta1, theta2, and w1, w2 be the rotations and the translation at nodes 1 and 2 respectively. No doubt, right? The expression for, I am coming to the discussion. The expression for transverse displacement can be in the form of a polynomial. Okay. Now we are going to assume displacement function. Okay. The displacement function we are going to assume. Okay. That is already we are choosing polynomials. Okay. So say the displacement W. This is W1, W2, nodal displacement at any point. Okay, inside in the element, say the displacement, the translation, the vertical direction, W equal to alpha 1 plus alpha 2x plus alpha 3x square plus alpha 4x cube. Why are 4 terms? 1, 2, 3, 4. Why 4 terms? There are 4 nodal degrees of freedom. Here 2 degrees of freedom, here 2 degrees of freedom. Totally 4 nodal degrees of unknown freedoms are there. Okay, that is why 4 terms must be there in your assumed polynomial function, displacement function. Okay, displacement model. This is called displacement model. I have chosen. Okay, now as the total degrees of freedom are 4 for the element, we have chosen 4 terms. Okay, now what is okay? This I will come to. This can be written. Okay, this W can be written in the matrix form. This equation can be, this polynomial can be written in the matrix form. 1x, x square, x cube, alpha 1, alpha 2, alpha 3, alpha 4. You know that, which is nothing but W equal to pi into nodal generalized coordinate vector. W equal to form matrix pi into generalized coordinate vector. This basic and all you know. Now I want to get derivative of it because I require theta. I know what is rotation theta equal to dw by dx. Okay, rotation. Slope is dw by dx. Vertical displacement is, translation is w. What is the slope? Derivative of it, dw by dx. Okay, theta is equal to. So determine derivative. Alpha 1 0 becomes, if you derivate alpha 1 0. Alpha 2x derivative, if you okay, differentiate alpha 2 plus, if you differentiate alpha 3x square to alpha 3x, okay, or alpha 3 2x plus, if you differentiate this 3x square, alpha 4 3x square. Okay, this is the differentiation. Now we can write now we can write this one. No, can you able to, no degrees of freedom you can write. Shall I rotate and show you? You have to see this. No, I will do one thing. I will rotate and explain this one. Longer rotate pantana. 1 minute. Is it visible? Yeah, it's visible. It's visible, no? Yeah, it's visible now. It's okay, good. See here, I will explain here. So what is the nodal degrees of freedom? W1. wherever x is there, you have to substitute x1. Okay. So alpha w1 equal to alpha 1 plus alpha 2 x1 plus alpha 3 x1 square plus alpha 4 x1 cube. Okay. What is theta 1? Theta 1 equal to the derivative you obtained, no? This one. Do you remember that equation? Alpha 2 plus 2 alpha 3 x1 plus 3 alpha 4 x1 square. Wherever x is there, you have to substitute x1. Next one, w2. W2 equal to alpha 1 plus alpha 2 x2. Wherever x is there, substitute x2 plus alpha 3 x2 square plus alpha 4 x2 cube. Okay. Similarly, theta 2 equal to rotation equal to, we obtained a derivative, no? dw by dx, we obtained, no? That one. In that you substitute wherever x is there, substitute x2. Alpha 2 plus 2 alpha 3 x is not x3, x2. 2 alpha 3 x2 plus 3 alpha 4 x2 square. Okay. Now this can be written in a matrix form. W1 W2 W1 theta 1 W2 theta 2 is equal to write down in a matrix form. 1 x1 x1 square x1 cube 0 1 2 x1 3 x1 square. Okay. And then 1 x2 x2 square x2 cube 0 1 2 x2 3 x2 square into alpha 1 alpha 2 alpha 3 alpha 4. Okay. This way we can write it in matrix form. Okay. This nodal is of freedom. Okay. That is the displacement at the nodes we have written from the assumed polynomial function. Okay. So that can be written in matrix form here. Its continuity is here. For simplification, let the origin be at node 1. It means what is the value of x1 at node 1? If you choose the origin at node 1, x1 0. What is x2? L. Okay. In that I substitute for simplification. I will rotate again. Right? Yeah. So for simplification, that's what. Let the origin be at node 1. Therefore, x1 equal to 0, x2 equal to L. Okay. Therefore, du, node d sub u is equal to w1 theta 1, w2 theta 2 is equal to, you substitute that one. 1, wherever x1 is there, substitute 0. So 0, 0, 0, 0, 1, 0, 0. Wherever x2 is there, substitute L. So we obtain this one, this matrix, into alpha 1, alpha 2, alpha 3, alpha 4, generalized coordinate. Okay, vector. That is nothing but du, d sub u equal to form matrix capital A into generalized coordinate alpha. Okay, that is implies, therefore, generalized coordinate alpha equal to A inverse into du. You know that. Okay, basic fundamentals. Generalized coordinate method, I am doing it. Okay, I am writing. By generalized coordinate method, we are going to derive the shape function for beam element. That's what I have written here. Okay. Now, what is n? Therefore, A is nothing but this one. This matrix is A matrix. I have written here. Okay. What is A inverse? We know that I have to write here. W equal to, what is W? Therefore, the variational displacement within the element. W equal to pi, that first form matrix into A inverse matrix into du. Nodal is a freedom vector. Okay. Which is pi into A inverse nothing but n into du. Okay, that is nothing but n1 w1 plus n2 theta 1 plus n3 w2 plus n4 theta 4. If you expand it, you will be getting. Okay, now I am writing this w is equal to 1 into this into A inverse. No, so A matrix is this, right? The only difficult part here is because there are so many zero coefficient. Easily you can determine determinant. Okay, that inverse for it. I advise you to practice. There is a 4x4 matrix. How do you obtain inverse for it? Okay, I advise you to practice it. Otherwise, there is no any other go. Memorize this one. Okay, during examination, because it's very important. Two-dimensional beam element development of shape function for two-dimensional beam element is very important. Okay, because many question paper I have seen development of shape function for two-dimensional beam element. In this, the difficult part is determination of inverse for this time-consuming part. I advise you to memorize this. No any other go. A inverse equal to this one. Okay, memorize this. Therefore, which one? W equal to form matrix pi into A matrix into nodal d sub freedom vector. Okay. Therefore, multiply this into this. Therefore, n1 equal to what? 1 into 1, 1. x into it is 0, 0. The next is x square into this one. So minus 3x square by L square. And then this into this. So 2x cube by L cube. Okay. Like that you are getting. Next, 1 into 0. N2 equal to, okay, continuity is here. Okay. N2 equal to 1 into 0. X into 1, x. Okay. Next, x square into minus 2 by L. So minus 2x square by L. Next, x3 into this one. So x3, x cube divided by L square. Okay, x cube divided by L square. Like that you have to develop. Next, multiply. Okay, multiply this into this one. So you'll be getting n1, n2, n3, n4. So shape function we obtained. Its variation also shown here. Its variation also shown here for your reference. Already you know. This is some simple discussion how it varies. So thus we have developed the shape function for two-dimensional beam element. Okay, two-dimensional beam element we have written. There are 4 nodal degrees of freedom. Okay, that's why we obtained 4 shape function for it: n1, n2, n3, n4. Next class we will discuss how to develop element stiffness matrix for it. Derivation of element stiffness matrix for the two-nodal beam element we will see in the next class. Okay, with this I will finish. I advise first to go through and write down, derive it in your own. This way only you can learn the subject. First listen to my video, understand, okay, and then take a piece of notebook and then you derive in your own. Okay, then only you can understand it. Okay, with this I will finish today class, right? Today we have seen this one. No, it's okay. The next class I will continue how to derive element stiffness matrix for two-dimensional beam element. So today we have seen how to develop shape function for two-dimensional beam element, right? Good. So I will record your names, right? I have recorded your names. Good. Full attendance. All of you are attending. Very good. Very nice. Okay. Almost all of you are attending. Very good. No absentee today. All 24 of you are attending. There are 24 students in M.Tech class. Okay, it shows 26, including me to know. So totally all 24 of you are attending class today, every day, not only today, every day. Okay, so M.Tech students are very sincere students. I really appreciate it. Okay, keep it up. I will first stop recording. Okay, 1 minute. Bye to all of you. Next class we'll continue. If you want to discuss anything, you can discuss. Few minutes more. Okay.